Ian, please
Thank you.
fire away.
Cheers, thank you. Hi everyone. So today we're going to talk about reliability. But before I start, well, this is me on the screen at the moment. So I just want to say that unfortunately it's one of them subjects that didn't have a lot of good graphs and pictures and so on to put on. But and when I rehearsed it today, it did take a while, so I will be going at a bit of a pace. So if you can bear with that a little bit, that'd be great. But I'm hoping that you will find the topics in it interesting, particularly if you're doing functional safety, and you're doing the reliability calculations, that sort of thing. So I'll very briefly just say that I started my working career on Teesside, ICI Wilton, like a lot of people, and then since then I went 25 years working everywhere else, and then only in the past 10 years did I return to Teesside, where I work from. But most of me, because of my past, most of my people I work for, my clients, tend to be outside the area. So I don't have, you probably don't. You won't know me from from working in Teesside. Right. So last time we looked at the SRS. This time we're just looking at the SIF reliability study. I'm hoping to do more of these if you're interested, and we'll just look at other activities in the safety life cycle, and we'll look in some detail of the typical things that either misunderstandings or what people go wrong, or terminology that's misunderstood, and so on. So this presentation is based on my experience as a technical authority and functional safety assessor. We have we're going to be looking at the reliability. We're going to be talking about 61511. That is always my guide, and there's things in here. Now, there's a lot of words in this presentation, but it is hopefully that will make a good handout as well. So if you ever, you've been downloaded from the InstMC site, all the information's there. Before I start, I want to say that I always want to remind you that BS EN 61511 or IEC 61511 has been developed by humans, and it's an international team that was involved in the first development of it, and that means that they came from varied outlooks, individual biases and personalities that you always have, varied competencies were in the team. There was national, company and individual objectives. There was varied opinions, and safety tolerances and compromises were made. And there's, as I say, there was different vocabularies and terminology from different parts of the world. And so therefore the document itself does have, and if you know where you're reading it, you can see them, these compromises and inconsistencies and discrepancies. But it's not perfect, but it's not far off. It is a good standard. Now, like English and other languages, the terms of words used in functional safety do differ slightly from company to company, sector to sector, nation to nation, and so on. And a lot of terms have sort of like developed over time as well. They've become accepted terms, and some of them I can't trace where they come from. But I would always say to you is, does the terminology make sense? And I'll take one example. This subject is often called SIL verification. Now, it's used throughout the industry, that term. I use it because I know that people understand if I say it, but it's not ever referenced as that in any of the IC or ISA standards. I'll be clear on the standard. In the definitions, it's an activity that's it's not a verification activity. It's not a phase 9 activity. It's a phase 4. It's to do with design, and the activity is not to verify the SIF achieves the SIL. In fact, all it does is just looks at compliance of a small few items. That's all related to the SRS. So there's a growing number of people within the industry that are now starting to use the term SIF reliability study. And I think that's a far better description. But again, it's not in the standard, so you can use whatever makes sense to you. Now, the standard clause on failure rate, and we're going to talk about failure rate here, is that the reliability data used when quantifying the effect of random failures shall be credible, traceable, documented, justified, and shall be based on field feedback from similar devices used in a similar operating environment. Now, I've highlighted what to me are the key words. Credible, traceable, documented, and justified are not just keywords for this activity. They're keywords that you should use throughout functional safety. Whenever you're doing work, whenever you're asked a question, whenever somebody puts something in front of you and say, is this okay? Ask yourself them questions. Credible, is it traceable, is it documented, and is it justified? Because that's what people who do functional safety assessments will be doing if they're doing it right. And certainly the regulator will be doing that. The field feedback one, well, we'll cover that in a slide or two. Now, there's many failure rate sources available. I'm sure you've used a number yourselves. And, there's what we call field data, like ARIDA and SIF, which, is drawn from, particularly ARIDA, which is offshore. It's taken from their databases, and they do analysis on it, and they come up with some values. There's laboratory destruction testing, which was in the original days, a long time ago. That was one of the few things that there was before, when this standard first came out. And that was very usually military funded, and it was usually on a component basis. Still used by the manufacturers. Failure mode affected diagnostic analysis for MEDA is very popular, particularly with Exceeder. And there's nothing wrong with it. Customer feedback. Well, I would say there's cases of customer feedback. I know everyone goes, oh, not customer feedback. There is cases of customer feedback where it is actually a good source of information. If you are Rolls-Royce and you are selling an engine to a company, you will have such a close relationship with, and you'll follow the life of that engine, and the data that you'll gather, and the data you'll gather from all the other engines that you sell, will be fantastic. But unfortunately, we don't often buy aero engines. We buy instruments, and when they don't work, we tend to throw them in the bin, and the manufacturer doesn't find out. So yeah, it's manufacturing data. When you see on the certificate, based on manufacturing information on returns, then beware. A statistical compilation of above is that was at one time it was just the likes of Faraday would did that sort of statistical analysis of compilation of everything. But I've noticed the likes of Exceeder are doing that more now as well. Each source, now everyone says which is best. Now the question is each source has its good points and its bad points. The field data tends to be more conservative, but it's more conservative because it's built in with loads of systematic failures, which you don't really want in there. For MEDA, tend to be it's a bit truer to the focusing on the random failures, which is good. But have they covered everything? Again, it's human analysis. There's errors with humans. So how do what would the regulator be looking for? Which one? These are just these are influencing factors. There's lots of influencing factors on this data. You can read that yourself. So the regulator ideally is looking for field feedback, data taken from the facility in question, accurately diagnosed and recorded, good practices for identifying systematic failures amongst the historical data, causes of uncertainties identified and assessed and accounted for, and an upper bound of confidence of 70% for each reliability parameter. Number of sites I've seen with this, 0%. Nobody's doing it. It is very, very difficult. I've seen many attempts, different ways of doing it, and they've all failed. I have built up my ideas of how possibly this could work, but unfortunately, it's taken me a lot of years to see all these failures, and now to think, oh, I think I now know the solution. But how would I know? Because it would take years and years of collecting data to find out if we're on the right track. So, so the chances are that you're not going to have that data. So here's another way of doing it. Always start with certified data. That gives you the traceability, particularly if it's from an independent, trusted organisation. And then compare that certified data with other sources of information. Compare it with your field data that we talked about, a reader, with your likes of SIF, generic data, and FAMIDA, and so on. Ideally, another certified device. Look at a certificate of a. If you've got a Rosenberg transmitter, look at an ABB transmitter. How does it compare? This is sensitivity analysis, and this gives. And if you can find that the data that from the various sources is within half a magnitude of order of each other, that is credible. Now, if it isn't, if your certificate data is a little bit out, but the others tend to agree, then this is where engineering judgment comes in. And there's nothing wrong. You have to ask yourself, is there a reason why my let's say it's too optimistic? Is there a reason? Maybe it's a new technology, less moving parts, less you can give a reason for why this is more reliable. If that isn't the case, then maybe add in a biasing factor. You can come up with it yourself, as long as you justify it. Remember the key word, justification. And keep the whole process documented. So we've got traceable, it's credible, justified, documented. The regulator will be happy. This is just this is straight out from my procedures, and it just goes to show how you can compare. It was a graphical way of comparing data. The first one shows everything is within half a magnitude of order, and that's in the green area, no problem. The next one says, well, let's imagine that the first three come out and you've got one outlier. Well, get another bit of data and compare it. If if they're all sort of outliers, then take the geometric mean and maybe use that as your reference point, or move that as a comparison for your certified data. If you can't do any of them, then maybe have a chat with somebody else and see if you can come up with that, how to deal with the situation. Technical authority, if you have one in your company. Whatever the source, read carefully the conditions associated with the reliability data information. So, for example, if you're using SIF or Faraday, there's often, you'll see, oh, that's my transmitter, and there's the data. But underneath there's small writing. And that small writing is often telling you to do, saying, if you've got architecture like this, if you're using it in this situation, it gives you some further guidance, further ways that you've got to manipulate that data. And always, no matter where you get your failure data source from, always apply the requirements of the safety manual. Okay, we'll move on. I'm now going to talk about other bits of information that go into your SIL calculation. And this is the clause. I won't go into it. I won't read it all. It'll take me all night. But I've highlighted the areas that we're going to be looking at, and we've talked about some failure rate already. So, firstly, I've got a question for you guys. Question 1: what is the difference between random and systematic failure? Is it A, systematic failures are deterministic and not random? And random failures aren't. I.e., it fails given a set of conditions. B, systematic failures can be eliminated by modification, but random failures cannot be eliminated. C, random failure rates are more or less constant after burn-in and wear-out, while systematic failures are not consistent. Or is it D, all of the above? So, anybody want to decide which one of that it is? D. Does everyone agree with D? Yeah, D is correct. So, next question. BSEN 61511, section title 11.9. It's basically saying, what is the requirement? Is it to quantification of random and systematic failures? This is, this activity that we're looking at. Is it the quantification of random and systematic failure? Is it the quantification of random failure, quantification of systematic failure, or does it just say quantification of failure? Anybody? Okay, so it's quantification of random failure. Okay, so this is important because, and the reason it's quantification of random failure because you can't quantify systematics. Yeah, that is the basis. You cannot quantify systematics because they don't meet any of the things. They're not a constant failure rate, and on some sites there can be certain types of failures will be fixed and they don't happen because you can fix them and they never happen again. And other sites they will be there and they don't get fixed. So it's not, so from site to site, it's not even random. It's systematic.
What would be an example of a systematic failure? Poor installation or what?
So, a systematic failure is, as you say, poor installation. It could be blocking of an impulse line with liquid. See, let's say that every time you do a letdown or something like that, you block your impulse lines. That's systematic, yeah? Now, I want to talk to you about de-rating factors, and this is linked. These days, when you get these calculation models from the likes of Exceed and ABB, they come with these, and they're getting more and more de-rating factors. You get things like wet and dry factors, where you multiply the random failure rate due to the process condition or the environment. You get Site Safety Index, Exceeder, SSI, multiplication factors of random failure due to basically process conditions, so you're duplicating, and management and so on of that particular specific to that site. Maintenance capability index is another value that everyone uses, or not everyone, but people who use an Exceeder tend to use Excellentia. Again, more multiplication factors for random failure, depending on the ability of the system, the site maintenance team. So basically, if they're incompetent, you can give a low, instead of fixing the problem and getting them trained up, you can just, it's not a problem because you can just put a low MCI factor in, and change your random, and multiply it against your random failure rate in your calculation. That'll solve it. But does it? Before using any of these factors, these are all systematic failures. There's a tendency to be trying to shove systematic failures into your calculations all the time. How can a systematic issue have any relative relationship to a random failure? It doesn't. How does increasing the random failure rate improve the accuracy of your calculation? You're out there to quantify the random failure rates. That's what the standard is saying. You've been given a value, you've gone and found it's credible, and then you're making adjustments to it. Does it improve the safety by compensating for poor functional safety management? Well, not really. You just trying to compensate for it, but in a stupid way, really. Because, well, take for example, let's say you've got poor maintenance. Well, what will that do? You mark it down. It's going to increase the random failure rate, which is going to increase how often you're going to test it, which means that safety instrument is going to be exposed to them useless technicians more often. It is not the way to go. You need to you solve it by solving your systematic issues, solving your maintenance issues, solving your management issues, and so on. You do not just putting multiplication factors into the calculation.
What about the case if you've got a lot of site data that says that when we use our flow meters and say water, they fail a certain rate, and when we use them in acid, they fail 3 times as often, and we see that so often that we just multiply everything by 3 and there's some process contact. Is that not a valid thing to do?
Well, I would say again, it's more, that is again it's a question of systematic, isn't it? It's a question of why is it failing in acid.
The acid's eating it.
Yeah, so that's the acid eating it is a systematic failing. If you know the acid's going to eat it in a certain time, you've got to replace that meter more often. That's the way you fix it. Yeah, if you replace that meter more often, you fix it, and you won't have a random failure, or that particular failure. Yeah, so that's a systematic failure, and just testing it more often won't stop it from failing more often. Do you see what I'm saying?
There's a bit of that. I think there is a counter side. I
don't think there is.
It's just to stop you overclaiming your performance.
This is it. You see, this is what it boils down to. It boils down to people getting comforted by the fact that they think, oh, if I can put these factors in, it'll give me that little bit of comfort that I'm going to give a conservative value. Okay, and a lot of that comes down to what we were talking about originally, which was you're not that confident on your failure rate that you're using. So if you have done your sensitivity analysis and proven and got credibility to show to anyone that you know what your failure rate is, then you don't need to start adding times in by loads of other factors. Yeah, give yourself confidence in the failure rate you're using, and ideally, I mean, if you've got site data and you just know that, then yeah, I absolutely, but don't increase it, solve it. Don't start multiplying them. Solve the problem rather than. Because if it's wearing out, if it's degrading because you've got a thing, replace it.
But if you only get the opportunity every 3 years, every five years to make these changes, is it not right to acknowledge the fact that you're putting your instrument into a much more difficult environment, particularly if it's happening all over your site? Yeah.
I just don't see how it solves the. What are you actually achieving, though? Anyway,
you're time. Risk. You're saying, am I reducing the risk to people on my site?
But that's the thing. You know what I mean? Are you?
Yeah. I do think you've got to stick with the 2 factors.
Yeah.
So I'll ask a different question.
Go on.
Do you build systematic failures into your proof testing?
So do I build systematic
failures into your proof testing? As in correction and finding and straightening up of systematic failures.
Oh yeah, absolutely. You would. Sorry.
Guys, we need to put them in because we're trying to make sure people don't.
Right.
Yeah, that's what my experience.
That is because that is because we include inspection because inspection is a maintenance routine that you should be carrying out, which tends to look for systematic failures. Yeah. And we tend to include that at the same time as we do proof testing. So we join them together in the same procedure. But it's not necessary. But really, what the proof test is about, from a functional point of view, is looking for undetected dangerous failures.
Correct, but they could be systematic.
But if they are systematic and they're happening regularly, fix them.
That's the whole point. My experience, a lot of saying is that the maintenance technician does everything he thinks he needs to do. He's missed something.
Yeah, but just by putting a multiplication factor in your calculation is infecting your, what you do in your proof testing and adding them inspections in is good practice, but putting the factors in to your it's not achieving anything. Just at some point, all you're doing is you're just manipulating a PF.
I'm not belittling the reliability there. I'd be recognising that some people have a more robust process for checking and reviewing the documents they put together. Someone that does a lesser one. It's like
it's a hard one to accept. It's but it's one of them things that you've got to really think about. It's because it's really starting to really you have to start really thinking about. Well, what is systematic?
Can I ask myself that question? If I've got a car outside, the one that you're going to trust for in 7 years is the one that's got the greatest systematic processes, not the one that did the best reliability data analysis, but the systematic process, because that's what quality is about.
Oh yeah, I agree, and that's what functional safety is all about. Functional safety is all about managing the systematic element of it. And that was really that's what I'm saying. That's what you've got to do. You've got to do good functional safety management rather than trying to just compensate. Yeah. Okay, we're going to move on to a different subject: dangerous detected failures. Now, this is something that I always have said to people: be very careful with this. With dangerous detected, a lot of the time, it's fine, but be very careful. So, firstly, you understand that when you got your failure rate, and whatever it is, it's a quantity this big, and then you're dividing it up into your undetected dangerous failures and your detected dangerous failures. Now, the bit that you've said is now detected dangerous failures. When you look at the calculation, it's going to have no influence on the calculation at all. Because basically, all you're doing with failure rates on the calculation is you times them by a period of time. The bigger the period of time, the more influence it has. With dangerous detected, all you're timesing it by is typically 72 hours, 92 hours, where compared to the others, where it's timesing it by months or years. Yeah. So it has very, 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 very minor impact. Undetectable. Now, if your dangerous failure results in an automated safe state of that SIF, no regulator is going to raise an issue with that, and it's fine to use the dangerous detected failure within your calculation. However, we often find dangerous detected failure used in places which raise alarms. Now, there's nothing wrong with that in 61511 and 61508. Permits this. But the regulator or an FSA assessor is going to look into a bit deeper because the requirements associated with them alarms and what they're going to look for is going to be more challenging. So they're going to the critical. So when you've got critical faults that are related to a dangerous failure of a SIF, activates an alarm only. Firstly, we're going to say, is it from the alarm going off to the repair being made? Is it done within the mean repair time? Okay, no problem on that one. But that means somebody's going to monitor that. And, how do you prove it? Okay, if the regulator said, prove that you did it within the repair time. I've got that information. It's one of the things where you just, I don't have the information. We do. Honestly, the operator response is defined and understood. So are you really confident that when the operator gets a fault alarm, he's going to understand the importance of it, and he's going to take the action in such a way that's going to speed up the process to get rid of this dangerous failure, or at least to address it. Remember, you've only got your mean repair time. Are you putting compensating measures in place? As soon as the fault has arrived, one of the first things the operator should be doing is treating that as if an override has gone on. So, have you got a process that puts compensating measures in place to remove the risks? Is the alarm function part of the SIS? If your alarm is coming up on the DCS screen, it doesn't conform with 61511. Now, not people. This, and I've seen, you know, this. It's something I would overlook, to tell you the truth, as an assessor, but because it's I've seen it so often. But that's not what. But it's very, very clear in anything. It says that it has to be, the alarm has to be part of 61511, and it has to be managed under that that standard. And the alarm must be periodically proof tested. Now, these are very demanding. You've got enough to do. So my advice on here would be just don't go there. If you've got a diagnostic dangerous failure, but the only way that diagnostic, you can take credit for that diagnostic dangerous failure is through an alarm, I would just add that diagnostic dangerous failure to your undetected dangerous failure and use that value as, just use that in your calculation. Don't use it as DD. Okay, another subject, so I'm going to keep on moving.
Use a diagnostic flag like that and just say, I'm just going to trip.
If it's tripping, it's fine. If the operator is told to trip, that's fine. And it brings up a good point. I mean, I was brought up an example the other day, okay, where they were using a partial stroke test. And it was an automated partial stroke test, and I said, okay, so what happens when the alarm goes off? Because they can't really shut down, because if the valve's not working, they can't do its job. So, but let's say your partial stroke test raises an alarm and says, I can't work. The dangerous detected fault. And in this particular case, I said, well, what happens? Oh, well, we have to report it to management. Why do you have to report it to management? Oh, because that shuts the whole plant down. Yeah. Now, what if the management is under stress at that moment in time? He's under pressure from his management or from the government saying we need gas. There's a shortage. The country's under stress. What do you do? So the recommendation for that particular customer was that they should have it written down. They should get management in, and they should decide now, while they've got clear heads, what the action is, and have that written down, as you just said, and that's what the operator does. In that case, the alarm would be perfectly fine. Okay, moving on to MTTR. Now, this is one of my little bugbears, this one, so I couldn't help but put this one on. Here's a question. Many software tools use the term MTTR. What does the abbreviation mean? Is it mean time to restore, mean time to repair, mean time to recovery? Anyone? Repair. Mean time to repair. Yeah. So software tools, they use it mean time to repair. In BS 61511, 61508, and the ISA standard, the American standard, what does MTTR stand for in this case? Mean time to restore. The two are completely different meanings, yeah? And now let's look at the difference between them. Right, let's start with the mean time to restore, okay? So the mean time restore is the time to detect the failure. So typically that's like half your proof test interval, but let's say you're using a partial stroke test, it could be, let's say even if it's automated, it's like half of, say it's 30 days, that'll be 15 days. Then it's plus your MRT, that's your mean repair time. It's that's the time to do the repair and get back into operation. Okay. Now let's compare it with mean time to repair value. Okay, and the mean time to repair value is a little bit different, because when you read the definition, it's the average time between the occurrence of the failure and the completion of the repair or failure, and it must include, and it gives it's the same three things that are in the mean repair time. In other words, the mean MTTR in the mean time to repair is the MRT value. So you see they're actually two completely different things. So why do they use that value? You know, if they mean two different things, what do they actually mean? Well, when it all comes from the same source as the SIL verification word comes from. It's the ISA technical reports. So these aren't standards; they're just guidance, and it's them reports that use keeping raising these words and changing meanings, and when they're doing it, they're doing it under an example where the diagnostic sample rate is so small that basically you can discount your time to detect. So you discount that, fine. So most of the time it's okay, because most of the time when you're using Lambda D, it's done in electronics, it's all fast, and so when you times it by mean time to repair, which is the 72 hours, it comes out right. But as soon as you start using it on things like partial proof testing, which is what most of the applications, software applications that do self-calculations do, you now got your MTTR is no longer 72 hours. It's that 30 days. It's that 15 days. You know, it's half the test. It's no longer insignificant, and the MTTR value is now incorrect, and that can cause a lot of confusion. Plus, I hate the fact that they use, and I don't know if it's changed in the new version of Excellentia. I think it has, but on all the older versions, they've taken a proof test into the proof test coverage of a partial stroke and shoving it into Lambda DD. Remember how I showed you the first calculation, how it has no influence then. But what you really want is what you really have is a Lambda DU what it should be is times by a partial your proof test coverage. That's what it should be, but they fudge it because that's the way they because they haven't got the calc to do that, so they fudge it. So be very, very aware of that. The regulator will find that one if it looks at SIF with that on. How are we doing for time? Oh, not too bad. Okay, move on to a different subject now. Proof test coverage and mission time. Okay, so we mentioned proof test coverage last time. Proof test coverage is the factor which describes the percentage of the component's dangerous undetected failures that are revealed by a defined proof test method. And this is where it gets, I've underlined defined because this is where you start to, when you do your SIL calc, you need to know the method that's been in use, you know, for your proof test. Sometimes the proof test procedure hasn't even been written then. But that's not a problem, so long as you refer to the safety manual, because they should really define for you what the proof test method should include, and then give you the proof test coverage. And if you do that, that's fine. And so, you know, so there's an important link. Now, the other thing is, proof test coverage is only good if you use it with mission time. Okay, and we'll look at that in a little bit moment. But so if the manufacturer stipulates or recommends an overhaul frequency for, let's say it's a valve, then that would be your mission time. It's the time, or if you if you decide because your meters are going to get all acid and corrode, your mission time would be the time where you know it's going to work successfully. Now, here's a sort of you'll have seen these before, but I think it's worth re-looking at them, because it shows you the link between proof test coverage and mission time. The first one shows the typical sawtooth diagram. I'm sure you've all seen for your proof test, for a typical proof test, ideal proof test where you've got 100% coverage. So you start at 0, and on day 1 you've got a brand new equipment, you've tested it, and you start it, you walk away, and the probability starts to increase. And then at some point you go back and you test it, and you get a 100% test, and you know it's working, and you're confident again. So your probability again is now 0. You walk away, and the probability starts to rise again. And it's easy to take a PFD average because it's just half of your proof test interval. Now, if you were to not have a proof test, if you don't have a perfect proof test coverage, and you look at the graph now, where each time it doesn't reset to 0 each time. Your average is a moving target, and the calculation can't do it. The calculation only really giving you is the point is the end of the first sawtooth. Okay, and the only way you can get the true average now is if you include emission time, a point in which you bring it down to 0. That is the point. That's when you can start to average it out again. You've got a datum point where you can average it out. Now that point when you bring it down to 0, that could be, as I say, it could be overhaul it, or it could be replace it. Okay, and your calculation needs to take that into account. I would reject any calculation that used the top one. It would have to, that just use the simplified equations and assumed 100% coverage. But unfortunately, that is I see it too often. So we've described what mission time is. Now I'm going to talk about some failures. Now first is the failure, in my opinion, of the standard. The standard 61511. Well, 61511 doesn't say anything about mission time. It requires that you do your proof test coverage. That's in the standard. So, but it doesn't say anything about mission time. So, as I said, the two go together. And it may not always be the term mission time, by the way, is not a term that is a constant. Other people use different terms. But as long as you understand what I'm meaning. 61508, the sixth book, I don't know what you call it, but I call it -6, which does all the calculation, shows you all the calculations. That does, towards the appendix, that does cover non-perfect proof test. But basically, when you read the words, what it says is your mission time is the point where it fails, and you have a hazard. That is your mission time. That's the point of, that's what they call T2, is when will only be, they're saying basically the undetected failure part, the undetected failures that you haven't been testing will only be revealed when a demand is made on the safety system at the demand period T2, and that demand period T2 is the interval between demands. In other words, a demand. Now, if it's an undetected failure, that means that SIF's not going to work on that demand, and therefore it's going to be whatever comes next. Yeah, loss of containment or whatever. I don't think that's good enough, personally. So, I think it was Exceeder. And I've criticised them a little bit in the last few things, but I think they were the ones who often use the term mission time. And I think that it's good that did that. However, on the other hand, where I have seen mission time being included in software, it is often misused. So there's failures in the software. They misdefine it for common. I've read one just the other day. It was an older version of Excellentia, and the description of mission time is the fact that it's the expected life of the facility. Well, it isn't. It's the expected life of the device, and you couldn't say, okay, well, I know what it really means. You couldn't say, because you only had one mission time, and it was for the whole SIF. So you couldn't do it on a device-by-device basis, which is wrong. You need to be able to do it on a device-by, because your transmitter will have a different mission time to your valve. So the software applications aren't ideal. Again, I do believe that they are improving this. Then, as I said, there's failures of the users as well. Too much using of 100% coverage. Now, I will agree with you on times. There's where I've seen, you've got a level switch or a pressure switch, and it's just a switch, and they give and the manufacturer gives a test point. When you test it, a proof test coverage of 98%, and I think, what is the last 2% on a switch? And I know people who've challenged the manufacturer and they've never come back with a decent answer. So I do care, but at the end of the day, that's, working on traceability and documented. If it says that in the safety manual, we've got to use it. And I'll give you an example of so often we use rose mounts, for example, 3051s. And how many know that if you use the better proof test coverage that's in the safety manual, it only gives you a 90% proof test coverage. And yet, the useful life of that device is 50 years because it's got these new super duper capacitors that don't burn out and or don't dry up like the old ones. But if you're only doing 90% proof test coverage, or in other words, you're not doing 10% of your undetected failure rates, that device is not going to last you 50 years. You need to replace it at some mission time before then, yeah? Some time when you can say, because that PFD is always going up. I can no longer achieve my PFD because there's these known undetected failures that I haven't been able to test in the last 10, 15 years.
So for example, if you've got a high temperature trip and you say, when I carry out my simple proof test, the first thing I do is to bypass the RTD and a connected resistance box, and I try to test everything from that. But if there was a problem with my RTD, I wouldn't know, and I'll do that test over and over again, and I still won't know until maybe after 10 years or 15 years, I take it out and thoroughly calibrate it and maybe replace it. I guess you have to make a judgment as to what do you claim for the proof test coverage for that not totally adequate proof test.
Yeah.
And you then set the mission time in that case at 15 years.
Exactly. Yeah. So if you can take something out and give it a good overhaul, like a solenoid, you take it out, you change all the seals, that sort of thing. You can give yourself a lot of confidence that you've now reset that, and it's as good as buying one off the shelf. And you should say if you do these things, you can say that's your mission time. You've done that. And you can, so you can take credit for that in your calculation.
Yeah, the solenoids are usually just fully tested and a process. I'm thinking of trip initiators where you think I'm not going to be allowed to take the process up to a dangerous temperature. So
No.
So I know I'm systematically not testing that.
Yeah.
On a much longer time scale, I take it out altogether and replace it or recalibrate it.
Yeah. No, I mentioned proof test because I mentioned I mentioned solenoid valves only because I know from the safety manuals of them that they have a proof test coverage of, which is not perfect, and they have they tell you to remove them every so often, replace all the seals on this spindle. If you do that, then you can put it back in and it resets.
Just so I've got a mission with 3051s at the moment. How do I get 100%? Or if I had a 3051 and I've used it for 10 years and I change its GP and I commission that new SIF, I'm not that simple, am I?
No, you can't. You're not.
You never, with a second-hand piece of equipment, test that to a clean bill of health.
Exactly, yeah.
Every single piece of second-hand equipment can never give you a PFD that you start with.
Yeah.
And a lot of us are working on old plants that have got existing equipment, and I'm carrying out a SIF calculation on a new SIF with existing equipment.
Yeah.
that I don't even have a clue how many times it's been tested or how long it's been in service.
Exactly, that's right. Yeah, this is the problem. Obviously, these are the challenges.
Yeah.
Now, in many respects, that 3051 will be perfectly good on a control system. You could.
Yes, yes.
You know what I mean? So, I would just say, from a safety point of view, try and keep, maybe replace that transmitter with a new one, but to use that other one. It's still a perfectly good transmitter. Use it somewhere else. That if you want to, to get the best value, see if you can use it somewhere that's not safety.
I'm trying to apply this to legacy systems where
I know.
I don't want to dip in my pocket and replace all my 30, 50.
I've
got 50 or 60 or 150.
Yeah.
500.
Yeah.
That's a lot of money.
It is a lot of money, and that's a business decision. But remember, that's non-compliant. So there's non-compliance, but it's a non-compliance that has to be accepted by the business. It's not your job to accept that. Or hopefully, you need to, or at least you need to make them aware of this is what we should be doing. If they say we can't afford it, you explain it, and they come up with the decision. That's fine. But they've made, you've got, in your emails, you've got it written down. They've made that business decision against the non-compliance. Try and raise non-compliance. I tend to keep on my non-compliance systems, and we have them out and we write them down, and we read them. We have lots of non-compliances, and we live with.
Have ever thought about the PFD not starting from zero, which the equipment isn't in?
Yeah. All right.
Cases, especially in legacy equipment.
Yeah.
So
No, that's right. And if you don't know where it's come from or its life, you don't know. Yeah. You got an idea, but probably with the model. Yeah.
I think if you take the stuff like Ian said earlier on, you just start to always come in as your field data. And what performance is saying on your assets. So the regulator won't just accept you going, it's all. The regulator's going to know, are you tracing it? Because you fall back to Ian's point. If you're not tracing it, you're not looking at it, and it's old, you kind of back yourself into the corner that you've got to replace it.
Yeah, but if it's only 10-year-old, 5-year-old, and it's modern, still certified equipment that we've replaced due to breakdown or maintenance, and now I'm catching up with the legacy equipment, and I do a SIF demonstration on it, I can't start at zero.
Yeah.
And I don't know what number to start at.
Yeah.
Apart from maybe applying a 10-year age on all of these and saying I've only had 90% test coverage, and these now fall into
I did a job on an asset where the asset didn't want to change the valves. And so we modified the vessel, bring it back into service, rebuilds. And at the time, the agreement was change all the valves. So I said, well, we'll change all the valves because it needs to run for another 15 years.
Yeah.
Right. 3/4 of the way through the project, the mechanical engineer steps in and goes, hold on a second, that's going to cost a lot of money to replace all the valves. I said, yes, but that's what we agreed to do. So in the end he said, these valves were bought, it's a bit like Ian said, with a 25-year life, and they were about 15 years old. So he said, I don't think we should replace them when we could. And I did raise the question, it's back to Ian's point about ideal proof test coverage. I said, you've been doing functionality tests. Yes, I know the open and close, but do you know the seal? I said, the job of the valve is actually to seal, not to move. It wants to move, but it has to seal. In the end, long story short, I ended up with the mechanical engineer agreed to do a little pro forma to test and give some kind of coverage, and it included doing leak-off tests in situ. 80% of the valves failed, and he had to replace them. He had to. Just had to. But that's the thing, I think, what Ian's telling you. You need evidence. You do need some, one way or another, you need some evidence. You've either got performance history that justifies keeping in service, or you need to do some form of maintenance to establish you've got some credibility.
The 3051S's have, you come to think of them as very competent, capable pieces of equipment. I shouldn't have to do anything with them, but now we'll find out that if it's 10-year-old, the reliability data is no longer valid.
Certainly questionable, unless you've got evidence to back it up.
If they say you only get 90% just by how you test it, how do you get the 100%? You don't.
I find it interesting that we just come back from one of our overseas sites and they thought the trip systems are fine. Exceeder wrote a report that said that they're all verified, and they were in 2006. But if you look at the graphs, and they've done their sawtooth PFD graphs, or ramping up against a 20-year mission time. So for about 10% of these trips today, according to the report you're relying on, the ones that need to be SIL 1 are now SIL not.
Right.
You can see it on your own graphs.
Yeah.
You haven't looked at that since 2006.
Yeah.
So it was useful for getting the point across
Yeah.
that if you just leave all of this kit alone and you only do the proof testing,
Yeah.
at some point you're clearly not getting the reliability that you
No.
think you're getting.
That's right, exactly. Yeah, absolutely. So the last subject I'm going to cover tonight, it's not a big one, but I found it's an interesting one, or at least it was a question from a client, and you know, it was one that sort of like I never thought of it, and then when I did think of it, I thought, oh yeah, that's not. This is interesting. So what it was, it's basically, you know, all these software packages, they always group it into the the sensor element, the logic solver, the final element, and then you've got all the components. You've got to put them into one of the other category. And he was like, well, which is the best way of doing it? Yeah, where's the boundaries lie? Because don't specify that. So typically, I would say of all the people, all the companies I've seen, all the sites I've been to, the first one is your most typical. Okay, your input subsystem is sensor transmitter barrier if it's IS, and your output is your solenoid valve actuator and ball valve, and then the middle is logic solver is everything in between. Now, I looked at the client I was talking to. We was saying, well, they were asking, could it be done this way? And the answer is obviously yes. You could include the input card into the sensor, and you could include the output card into the actuator, into the final element. Now, which one gives you the most accurate result?
It can make a big difference if you don't always test the trip wet end to wet end every time all the way through. And so you test the front end more often than the back end. Then you have to think very hard about when does the middle get tested.
Yeah. You've hit the nail on the head there. Yeah, it is. It makes a difference if you're testing the sensor element more often than the final element, all the subsections. If your testing intervals are significantly different, it can make a big difference. Not massive difference, but it can make a difference. And therefore, you've obviously got to know the way you proof test. If you tend to proof test from your sensor all the way to your logic solver, and from your logic solver all the way to your ball valve as two separate proof tests, then and you do them significantly more important than you test your logic solver, and which I would question if you're doing that. Is there any point in doing your logic solver? But if you're doing that, you will get a better PFD, and you include that into your breakdown of your subsections. You think you will get a slightly better PFD. If you're working on a job and you just cannot achieve that target, it's one way to get a little bit more. That will might get you over that limit. I thought it's a nice little one to include. I wouldn't be bothered if whichever I saw on a site if I was just doing an assessment.
It works better like that with the voting arrangements we find.
It does. It's more realistic, isn't it? Really. Now, as for the testing the logic solver, that's a massive subject that would take another hour, so I won't cover that.
You go back to your first thing, then once you throw the logic solver and you go back to what about your systematic?
Yeah, exactly.
I've seen enough systematic failures that
Exactly, that's right, exactly. Now, it's summary and conclusion. So, firstly, I would say this: we've hit quite a lot of topics tonight, and I've gone quite quickly. And we haven't really had the time to debate them much, and there's even plenty more we could discuss even more, including that one we just mentioned about. But there's the beta factor, or sometimes I like to call it the beta fudge factor. The architectural constraints. Does the standard really oversimplified that? either of them. They've slightly different approaches, 61511 and 61508. But there's a lot goes into the thought of your architectural constraint, really, and I think they've avoided that. And systematic capability, it's these number of times I see reliability studies without taking into account systematic capability. This week, again, it was another one landed on my desk, and it's one of the problems is it's so easy on some programs. I think in all of the programs really, they can just switch it off. You can just go and say, "Oh, I'm not doing systematic capability," and switch it off your application. Excellentia, ABB, I think is the same. You just don't. I'm not going to do it. But it's a normative requirement that you should identify the systematic capability, and it should be the devices altogether in the SIF. It should achieve the systematic capability level appropriate to the SIL, your target SIL. Some people have said that, oh well, we've used and certified data, and it's SIL 2. We've got SIL 2 certificates. I said, okay, well, you've got a SIL 2 certificate, you've got a safety manual. Does it give you this? It should, if it's been done since 2010, should give you the systematic capability. And there's still a lot of them don't. Do we take it as read? Oh well, if it's achieved SIL 2, it must have it. It must be appropriate. I would suggest it isn't actually. I would suggest that if anyone had gone through any manufacturer had gone through the process, the 61508 process of doing a systematic capability assessment, with an independent body, then they would have made sure that was in the safety manual, because they could have paid good money for that. So now, at this moment in time, I mean, a big chunk of the standard is all down to goes on about proven in use and what's the other term? Prior use. Now these terms are all about systematic capability. That's what they're there for. They're not about determining the failure rate or anything else. If you don't think it is, read the standard again. It's about determining. It's about if you haven't got systematic capability, then you're supposed to use like a prior use case. So it is a big issue. It's a big part of 61511. And yet I would say more than 90% of the reliability studies, I say, do not include it. So I'm going to summarise. So what's the point of this talk and so on? What am I trying to get across? Well, I'm trying to get across that BSEN 61511 has been around for 20 years, and 61508 has been around even longer. And yet we still continue to be on a learning journey, everyone. And as we navigate that journey, what I would advise is be aware of the potholes and the fact that there are a lot of well-trodden paths that lead in the wrong direction. So just because other people do it that way doesn't necessarily mean it's the right way. Continually refer to the standard as your guide on the journey, and be sceptical of those pointing the way, particularly if it benefits their company. A lot of these, as I said, indexes that you've got now in these calculations, they're thrown in as like unique selling points for them companies. And now you can include this rating, this D rating value, you can include this one. So always keep your mind open is the thing. Even this presentation, analyse what you've heard, debate amongst your peers, and always feel free to challenge me at any time, to come back to me. I'll leave my cards, my contact details are here. So I'm always happy to talk about it, debate it, listen to, if you say, well, I've been thinking about what you said on so-and-so, I don't think you're right. we'll talk it through, and then you'll soon find I'm right, after all. Just joking. So sometimes I learn, you know, and I try to learn all the time, because as I say, it's a learning journey. Thank you.